Okay, thank you very much for the introduction. And hello again, I'm Yihan. Today I'm honored to present our paper titled Mitigating CPU Frontend for Complex Data Plane Applications. This is a work from Xi'an Jiaotong University. Thank you. So the utilities of modern network is implemented by a wide range of data plane applications, or DPI we call it, like firewalls, software routers, and load balancers. And as recent networks are getting more and more complex data plane applications, or we call CDPA, have emerged to meet the needs. For example, various traffic pattern requires careful intrusion detection and prevention. Proxies often read application-level features to better distribute the traffic, and middle boxes in core networks need fine-grained control to ensure the QoS. So such transition is made because CDPAs require significantly more features. For example, they may have to parse a variety of network protocols, reassemble payload for further actions, matching payload against various patterns, and track all the states during all those procedures. And as a result, CDPAs are usually limited in throughput and require a lot of resource to scale, contrast with their simple ones, which can scale up to 100 GPS per core, and as in our previous presentation, even terabytes per second if you use certain hardware. Oh, sorry about that. So let me start with this slide. So, however, we wonder if complex processing is the only reason that accounts for the low performance in CDPAs. So with this question in mind, we profile the instruction per cycle, or IPC, of a set of simple data plane applications implemented with click elements as well as some popular CDPAs. So the results show that the IPC of CDPAs are significantly lower than the simpler ones, indicating that the CPU is not working efficiently. This suggests that there is a microarchitectural factors under the hood beyond the complexity in the processing logic. Further profiling characterized the application performance based on top-down microarchitecture analysis. Such analysis tracks the CPU cycles and categorizes them into four kinds: front-end, back-end, or bad speculation bounds, where the CPU time is wasted during fetching code, data, or the branch misprediction. And finally, we have the fourth kind that is retired, where CPU cycles are actually spent on the actual tasks. From the profiling, we quickly have a surprising finding. That is, those CDPAs uniformly show their biggest bottleneck in CPU front end, which is 45.1% on average. This is a direct sign that code access is becoming inefficient and preventing those applications from running faster. We then show that such inefficiency in code access actually stems from the typical packet processing pattern. As in this illustration, applications usually receive a batch of packets, processing them, and send them out. Here we use different colors for different parts in the code so that we can see which part is actually loaded into the iCache. So in the classic processing pattern, a packet starts its processing only after the previous packet finishes its processing. And this creates a problem. When the first packet finishes processing, the iCache will be loaded with the most recent instructions shown in yellow. Well, the next packet will start processing from the very beginning in the code shown in red. When the processing path is too long to fit into the iCache, cache misses will happen. And this will happen not only at the very beginning, but throughout the processing. In this way, iCache is not able to load the upcoming instruction and starts thrashing. There has been some existing method targeting on optimizing iCache performance on applications. The first kind targets on this issue by aggregating frequent function callers and callees, as well as related code blocks together in the application binary. Doing so, we reduce cache misses because the single cache line is now better utilized. However, under long processing path, such method is ineffective because the content in the iCache still gets swapped out, no matter how well the binary layout is. The second kind provides some domain-specific hints, like L3 info is no longer needed in L7 processing, enabling more aggressive compiler optimizations. Doing so reduces cache misses because the unreachable codes will not be loaded into the iCache by other instructions anymore. However, compiler optimizations are unable to alter the original core logic and still keep the long processing path as is. Therefore, oh, sorry, I hit that again. Sorry about that. So, not very familiar with my laptop. So, therefore, we reach a conclusion that no work actually reduced long path-induced iCache misses on CDPAs. So, different from rearranging binaries or removing dead code in the related works that keeps the execution path untouched, we look at this problem from another aspect. Our insight is that iCache thrashing can actually be prevented when execution path is redefined. This is achieved when the previous packet stops processing before finishing. At this moment, the iCache is loaded with instructions that following packet can reuse. The same effect applies when the stop packet resumes its processing. At this moment, the remaining instruction can still fit into iCache so that the following packets can hit the cache. Following such insights, we built a system called NanoPipeline that integrates such workflow into existing applications. First, NanoPipeline consists of an offline analyzer that finds and injects what we call scheduling sites into the code. Those scheduling sites effectively partitions the code into several iCache-friendly stages whose code size do not exceed the iCache capacity. When packet processing hits a scheduling site, its processing is temporarily suspended and the control flow is passed to a runtime scheduler. The runtime scheduler is then responsible for saving the context, finding the next packet to process, and handling over to the next packet. Together, both of the components aim to schedule packets in a pipelining manner among smaller stages than before, and this is where the name of this project comes from. Ultimately, multiple packets will go through the same stage, reuse the iCache, and mitigate the front-end bottleneck. So despite the execution order of each packet is changed, the packets are guaranteed to resume from where they are stopped. In this way, the original processing logic of each packet is just the same as before, and no modification is made to the native code. Next, we will highlight some of the challenges behind this seemingly intuitive design. The first major challenge is about semantic consistency. This is because the shuffled control flow can override the variable values. We show this problem using a simple code snippet which finds the flow inside the flow table and creates one if the entry does not exist. The original workflow is quite straightforward. Packet 1 comes when the table is empty, so it just creates a new entry. Then, packet 2 from the same flow will be able to retrieve the entry and will not enter the if code block. However, things are a little bit different when a scheduling site is injected between line 2 and line 3. In this case, packet 1 is stopped before a flow entry is created. At this moment, packet 2 also sees an empty flow table and tries to create an entry, which is wrong. In this example, the behavior is incorrect because packet 2 sees wrong value for flow table and takes the wrong path, and thus we consider the key to ensure semantic consistency as preserving variable values. We solve this problem by first classifying the variables and handling each type of them. Here we use a slightly more complex example that involves both the states of the flow and the packet. First, we classify all variables into two kinds, the per packet ones, which can only be accessed by a single packet, and the cross packet one, and the cross-packet one, which can be accessed by multiple packets. As shown in the code, non-pointer function arguments and stack variables are per packet, while global variables are cross-packet. Such definition is passed to all variables via value assignment. So first, the handling of per packet variables are straightforward because only one packet can hold their reference. As long as each packet has their own private stack, the value of per packet variables are saved and restored during scheduling. Next, we will talk about how we handled cross-packet variables. For each cross-packet variable, we need to first find their read and write references. This is done at the LVM IR level, running the classic ADS analysis tools to mark the variable access on the program CFG, as shown on the left. After finding all references of a variable, we build what we call commitment window of each variable. This is a range that covers all CFG nodes between the read and write pair of this variable. Finally, after all commitment windows are marked on the CFG, there will be CFG edges not falling onto any of the commitment windows. Such locations are considered safe for scheduling sites because packets stopping here are not able to modify the previous variables and will only access the following ones in order. In this way, we actually find the location that enables scheduling while strictly keeping the original program semantics. The second challenge we are facing is the efficiency during scheduling. After finding the safe locations, CFG nodes inside one commitment windows is merged in the same code block, and scheduling sites can be placed arbitrarily among the blocks. In this case, injecting scheduling sites are intuitively easy because one can just guarantee all the stages are smaller than iCache so that each stage can be fully loaded into the cache. However, such naive method has a problem. Since the scheduling site involves in execution context saving and restoring, decision making, etc., its overhead is non-trivial. This is particularly impractical when the CDPA code tends to be 1 or 2 magnitudes larger than the iCache capacity, in which case single packet will hit the scheduling site a lot of time, sometimes over 100 times during its processing, and even negate the iCache benefits. We solve this problem by adopting a profile-guided partitioning policy. This is possible because, in reality, execution paths of applications are highly screwed, and static partitioning severely overestimates the stage sizes. Based on such observation, NanoPipeline first collects the path details from the real traces, including cache line consumption and entering time of each block, etc. And as the example on the left shows, we can clearly see from the profiling data that block 2 appears significantly less than block 3, but takes more cache lines if it is loaded. And therefore, block 2 is considered to be more cache consuming and less code reusing friendly than block 3. These statistics are used to further calculate the cost and weight of each block and identify the most frequent program path. And as a result, the number of required scheduling sites are greatly reduced, and a stage can almost always fit into iCache during runtime. Due to time limits, we are unable to address the detailed design, so please read our paper for more details. Finally, we show the evaluation results of NanoPipeline. First, we apply NanoPipeline to representative CDPAs shown on the graph and measure the improvement on their throughput. The results show that NanoPipeline can give a decent performance improvement ranging from 17% to 30% on the applications. We also apply the optimization mentioned in Reframer, which reorders packets according to their flow so that the data access can hit the Dcache better. In contrast, the performance gain is limited because these applications are bounded by iCache misses. And we believe these highlight the need to deploy optimization for different applications on their real bottlenecks. We also apply layout optimization in Bolt Optimizer. and find out that it does not improve the performance much, and sometimes even make it worse, proving our point that layout optimization alone is not sufficient for CDPAs. We also show the critical performance counters before and after our optimization. First, from the first shaded column, we can see that the iCache misses of each application are greatly reduced because the packets now run inside iCache-friendly stages. Then we observe that the retired CPU cycle ratio of all applications goes up, which means that the CPU is delivering more useful work than before instead of stalling. And as a result, the IPC is now higher. This indicates that NanoPipeline can make the application run in a more efficient manner on the CPU because they reduced iCache misses and the mitigated front-end bottleneck. Finally, let me briefly summarize our work. This work stems from the situation where complex data plane applications faces a performance bottleneck on the CPU front end. We then review that such bottleneck is a result from the packet processing pattern and excessively long processing path. Based on such finding, we build NanoPipeline to split the application code into correct and efficient stages, and experiment results prove that the performance improvement we get is indeed from mitigating the front-end bottleneck. That is all of this presentation, and please read our paper for more details, and I'm happy to take any questions. Thank you.